Okay, so we're going to look at the area of a sector. This is an IB topic. Okay, so we put it in here. I think it says actually on the timeline. Oh, actually it doesn't. So you can just put next to area of a sector a triangle. Area of arc length is part of 30-1, but the sector area a triangle area, that's just IB. So for example, in the diploma exam, we're not going to ask you an area of a sector question. Used to be part of 30-1, but took it out. So in any case, we are wanting to come up, first of all, to develop the formula, but really, you're just going to use it. You'll be given it on our next test, and then when you write your IB exams, you'll be given it as well. Pretty sure anyway. For sure, the area of a triangle version is on there. Okay, so remember a sector is a portion of a circle bounded by two radii. Remember that's plural of radius. And the arc joining the extremities of the two. So there's your sector. It's like a piece of pizza, right? It goes right from the center. So in order to get the area of that, there's a development here. I think about it more, just a rearrangement of this. In any case, just remember that this is the center. So the ratio of that angle to a complete rotation will be in the same ratio as the area of this compared to the area of the whole thing. Okay? You have to compare equivalent parts. They're not equal in number, right? But so this is one part of 360, and this is one part of pi r squared, the area of the circle, right? So if you think about it, you can look at this. I think of area of the sector compared to the area of the circle. That ratio is going to be the same as the angle of the sector over the angle of the whole circle. Well, we know the angle of the whole circle is 2 pi radians. So therefore, area of the sector equals, so theta of the sector, I'm just going to call theta, the angle of the whole circle is 2 pi radians. And then if I multiply through to isolate area of the sector, area of the circle is pi r squared. Okay, so then if I simplify this, pi divide out, you can show that as 1/2 theta r squared. So that's essentially what this is here. They just went circle angle and sector angle. They did it across, and I just prefer to think about it like this. In any case, this is the formula that you're going to use, and it will be given to you. But let's say you might be doing a question in calculus, all right, that doesn't have like another math course, and you don't have the formula with you. You can reason it out that way, right? So they're proportional to each other. Okay, so you can summarize here, if there's space, A equals 1/2 theta r squared. Okay, theta in radians. If we had theta in degrees, then remember over here, we'd have to use 360 degrees here. And so what it would be pi theta r squared over 360 degrees. So kind of messy, right? That's it. We're going to use it. Take a look at the first example. Okay, determine the area of a sector of a circle with the radius 6, sector angle of pi over 6. Okay, express it in terms of pi. So your area of the sector is 1/2 theta r squared, where theta is in radians, so that's pi over 6. Radius is 6 squared. So show that as an exact value. And then it is area, so it's going to be centimeters squared. Okay, so the 6 divides out and the 2 divides out. Okay, pretty easy questions, right? Remember, sometimes the IB material isn't harder, it's just new stuff, different stuff. Determine the area of a sector of a circle with radius 5.6, sector angle of 120, and then round to the nearest hundredth. So, in this case, area equals 1/2. Theta is 120 degrees, so we need to convert that to radians. You can do it right within the formula if you want. And it does say you can to give your answer to the nearest hundredth. So really, you can just put that into your calculator. If you do want to simplify this, or you say you found a radian measure outside, that's 2 pi over 3, which actually the 2's divide out, so that's pi over 3 times 5.6 squared. So that is area of a sector. There's some practice there. Now let's look at area of a triangle. Okay. So we know the formula for the area of a triangle is 1/2 base times height, or you might know it as base times height divided by 2. It's the same thing. We can use that as a basic trick to show that the area of the triangle below can also be found using the formula A equals 1/2 AB sine of capital C, where A, B, and C are the side lengths, and capital C is the angle opposite side, little c. So remember back to math 10, if we're labeling sides, we use lowercase. The angles opposite them are the uppercase letters. So this would be capital C, okay? Capital B, capital A, okay? So normally, right, we would need base times height divided by 2, right? We don't know what that height is in a triangle like this. It's not a 90-degree triangle. So we would need to know that or know an angle. So given this, say we know this angle, okay? Think about how we can get this side using trig. This is opposite C. What trig ratios use opposite? There's two. Sine and tangent. Right. Sine is opposite over hypotenuse. Tangent is opposite over adjacent. Well, I don't have anything here, right? So adjacent's not going to help me. I know the whole thing, but not in that right triangle. So I'm going to use sine. So sine of capital C is H over A. Solve for H, which is the height, not hypotenuse. So look at what's labeled. I labeled it H. You could call it X or whatever you want. So that's height. So now area is 1/2 base times height. We specifically used B for the bottom side there just to make the letters, the variables match up. But our base of this triangle, I'm using that horizontal base there, which is B. And my height is A sine capital C. Just rearrange, order doesn't matter. So 1/2 AB sine C. Okay, so you can use that in any triangle. It's just that sometimes you don't know the angle, right? So if you know an angle, and basically you need to know the angle and the sides that contain it. So you need side, angle, side. Okay, if you want to use this formula, if you already know the height of the triangle, then you would never use this formula, right? So don't try to make your life harder just because you won't learn a new formula, right? So in this unit, yeah, you're probably going to be asked once where you have to use it, but you need that angle. And back in math 10, when we did trig, we asked you to calculate the area of triangles like this, where you didn't know the height, but you knew an angle. So you basically did the formula, you just didn't realize that you were, right? You did it in steps. So back in those questions from math 10, you found the height in this part, and you found the actual number. Then you substituted it into here. So you've kind of already done it. It's just now it's a formula that you can use. Okay. So, example here, use the new formula. So an isosceles triangle has two sides both of length 8. And then the angle between the two equal sides is 65. Okay. So between, and sometimes we say the contained angle, is 65. Determine the area of the triangle. So as I said, we've got side, angle, side. If they're equal, it's isosceles. So this would be C, this would be A, and B. You can switch those around, it doesn't matter. So this, it doesn't matter if it's radians or degrees, because that's just sine of 65. So just make sure your calculator is in degree mode. You're going to keep it as degrees. So mode key, third line down, make sure it's degree. Okay, you're going to have to switch back and forth in this unit sometimes. Okay. So 1 divided by 2 times 8 times 8, which is 64, times sine of 65. Brackets. It doesn't say what to round to, and it's 0, 0. So I'm just going to round to the nearest whole number.
just looking at it because that's not a right triangle.
Right triangle.
Yeah, if you were to separate it into two right triangles, it bisects that angle. Because like I'm just looking at the proof for it.
Well, then you would have to get this height,
Yeah.
and you'd have to get this side, so you're gonna have to use cosine law to get this, cut it in half, then trig to get that height. Should work. A lot of calculations to do it that way, though, right?
Yeah. So you can just plug the angle in. You don't have to.
Yeah, exactly. Okay, area of a standard stop sign. How many sides does a standard stop sign have? Who's taken their driving test yet?
It's an octagon.
It's an octagon, 8 sides, yes. And they ask you that on your driver's, and they used to anyway. What shape is it? So. Not bad. Okay. Okay, so I drew kind of the octagon there, close. Okay, so a stop sign is a regular octagon, which means all sides are equal length, okay? And all those angles will be equal as well. We want to find the distance between the opposite flat sides as opposed to opposite vertices. So it's going through the center there. So this is going to form some triangles, right? That green triangle that I just drew, what's special about it? What kind of triangle is it? Isosceles, right? Because this is going to be the same as this. So there's my green triangle. That's going to be at 90 degrees as well. So if I have the area of the whole stop sign, how can I get the area of that green triangle?
What is that unit that you just wrote? What is that unit?
Oh,
millimoles? Oh, millimoles.
sorry.
Okay.
What do I do to get the area of the greens? Divide by 8. Okay, so area of the triangle. Okay. So the area of this triangle is equal to that. So we want to work backwards to find that blue side there. Based on that, when we think about this, that's base times height divided by 2 will give us this. Or we can, like this, if this we call A, this is going to be called A. We can use that new formula because what do we know about this angle in there? 360 divided by 8. Okay, or 2 pi divided by 8. So we can get that angle. So I'm going to call it theta of the triangle, central angle. 360 divided by 8. What's that? 45. Okay, so therefore, area of the triangle is going to be 1/2 a times a, which is a squared, sine of 45. So this is going to get us the side A. It's not going to get us that distance yet, but for right now, at least it gets us the the diagonal distance, and this is 58,248.75. I'll just copy that out. Okay, so let's get a squared by itself. It's going to be 2 times 58,228.75. Okay,
Can I
so
just do this with exact value?
yep, you can. Okay, remember what sine of 45 is as an exact value. You can do that, or you can just enter it in your calculator. So I've already got the area times 2 divided by sine of 45. Okay, then square root. I keep a bunch of decimal digits just in case I clear my calculator or something like that by mistake. Okay, so recopy that triangle. This side, this side. Okay, so those are isosceles triangles. We know that this complete angle is 45. So that means this would be 22.5. And now we can call this h if you want, for height of the triangle. And so we can use trig here, compared to that 22.5. Now, you don't have to use that one. If you know this is 45 and it's isosceles, then you could subtract it from 180, divide by 2 to get these angles. So there's more than one option. In this case, I know this, and I'm trying to find this side. So this is the height, and this is actually the hypotenuse of that triangle. So adjacent and hypotenuse, that's cosine. So cosine of 22.5 degrees is the height of that triangle over this. So again, you could go straight to this step. And that's already in your calculator. So you just take that, multiply by cos of 22.5. Okay, and then the distance across is double that. So therefore, distance between the flat sides calculator times 2, and then you can round it, and it probably says to the nearest whole number. It doesn't even say, right? Yeah, so it works out nicely to 750. And that would be millimeters. All right, so distance across. Okay, so that's in millimeters. Centimeters would be what? 75, right. 10 millimeters in a centimeter. Okay, third one, determine the area of a triangle with side lengths. So, this needs to be changed to a 6. Because, why? It would be easy. If it's 3, 4, 5, it's just a 90-degree triangle, right? So 3, 4, 5 that's a Pythagorean triple. So then, your 5 would be the hypotenuse. Your base and height would be 3 times 4, which is 12, divided by 2 is 6. Do it all in your head. We really want you to practice what you're learning today. So we made a typo on this. So just change that to a 6. Okay, we want the area with side lengths 3, 4, and 6. So 3, 4, 6. Doesn't have to be perfect, right? How can we get an angle if we know 3 sides? Cosine law, exactly. So use the cosine law to find one of the angles. It doesn't matter which one. Okay, who remembers the cosine law? Okay, doesn't matter what letters you use, but there's a Pythagorean theorem as part of it. Okay, and then whatever letters you use for your 2 sides with the contained angle. So if you use A and B, then it's minus 2 times 1 of each of them, 2 times AB, cosine of the side opposite the angle. The angle opposite the side you're looking for. Okay, so you know the B, and you're trying to find the side opposite. So I'm on mine, maybe I'll call that C. So so that's the cosine law for a side. You can enter the values and rearrange, or use the rearranged form. Okay, which is, you're trying to find that angle. It's the other 2 sides, the sides that contain it, squared and added together, and then minus the side opposite square. And then only A's and B's there. So the sides that contain C are 3 and 6. 4 is opposite. Okay, and you are expected to know sine law and cosine law. Okay, it's not on your formula sheet. So if you have the fraction capability on your calculator, this is where it's kind of handy because then you don't need brackets. If you don't have it, then make sure you put brackets around your numerator and denominator. fraction form, doesn't really matter. The second cos of that, okay, so then area is 1/2 A times B times sine of 36.3361, etc. Let's see on my calculator. So I've got to go back up some other work here, but that's why you keep a few decimal places. So I cleared it, so I'm going to do it again. So I'm just going to check. That's good. So second cos. Okay, so 1 divided by 2 times 3 times 6 times sine of that angle. And we'll go to 2 decimal places, although let's see, it doesn't actually say. So let's go to 1 decimal place. And this would be centimeters squared. All right, so that's an area of a triangle, any triangle, as long as you know 2 sides and the contained